Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start with the final lecture of this Transformers chapter. So this will be a long lecture, so bear with me with. So we will discuss mainly two topics today. One is the open delta connection, other one is the harmonics in Transformers. So actually the weightage in gate is very low for this because only once or twice the question has came and very easy question has came. So don't take stress over this topic, right? Very easy question will come. Okay, don't have to go too much into the details in this topic. So let's start with open delta. As the name suggests, one of the delta line will be open. Then how much power will be delivered by the transformer? That is what we want to know. Okay, what do I mean by it? So let's assume that let's assume I have a delta to delta transformer, right? Here, this is a delta to delta transformer. Now what if one of the coils get open circuited? If one of the coils get open circuited, then what will happen? Then basically, how much power will I be able to supply if still the three phase load is connected? That is what we wanted to know. Okay, so that is what is written over here. An open delta connection, also known as VV connection, is a three phase transformer connection formed using only two single phase transformers. Okay, instead of the usual three, the primary and the secondary windings of the two transformers are connected in delta configuration, leaving one legs of the delta open. Okay, so if the one leg of the delta is opened, then what will happen? That is what we wanted to know. Okay, so if everything is fine, okay, there is no fault, this delta is not open, everything is normal, then how much power I give? So what is the rated voltage, and current of phase? Okay, rated voltage and current of phase. Okay, so uh, what we know is, it is basically, let's assume that rated voltage and current of phase is VPH and IPH. Okay, what is the three phase power supplied? So three phase power supplied, like there are two formulas. S three phase, right? In the first case, this is the case one. When, like, this is the case one circuit diagram, and this is the case two circuit diagram. Okay, so my S three phase will be equals to S three phase will be equals to basically this root 3 into VLIL, right? This we already know. Also it can be written as root 3 into VPH into IPH, correct? So this is the capacity for a normal delta to delta transformer. This is the load capacity. So I will write here three phase is three phase 1 in the case 1. So I will solve for the case 2 now. Okay, what is happening for the case 2? Things will be very interesting, right? Because for the case 2 only two phases will be there, any two phases will be there, right? So let me solve this case 2. In case 2, if I see that three phase load is connected, but what is the voltage VAB? VAB is still plus VA only. So VAB voltage is still plus VA. So VA angle 0, whatever the angle is. Okay, what about VAC or what about VCA? VCA is still plus VC. VCA is still plus VC. So VC is BC. What is the angle of VC? Angle of VC will be, it will be same as sorry, magnitude will be same as VA. Angle will be plus 120, right? Phase sequence is ABC. ABC phase sequence. Remember, this is my phase sequence. Okay. So what is VBC though? Can you tell me what is VBC? I cannot use this. This is open circuited, right? So I have to go by this loop. So VBC, right? I will find out VBC. So this is, let's assume this is VBC. So this will be plus minus VBC. Plus minus VBC. Okay. So plus minus VBC. So plus minus VBC, I will start from here, go to here, and then finish. So this will be minus plus VA, okay, and this will be minus plus VC, okay. So minus plus this. So this will be VBC will be what? VBC will be so minus of VBC minus of VA minus of VC equals to 0. So VBC is basically minus of VA plus VC. Okay, that is what my VBC is equals to. Correct? Okay. So what is this? What is VC? So VC is minus of VA plus VA angle plus 120. Correct? So it is VA angle plus 120. Now, what will be this equals to? So this will be equals to actually VA only, or no, this will not be equals to VA. So this, right? So VA is here, and VC will be 120 degrees apart from it. Okay, so basically, like, this angle is how much? This angle is this angle is 60 degrees, right? So it will be VC cos of 60 and then VC sine of 60. So VC cos 60 is I guess half only. Correct. So here I will have VA, sorry, VC, that is like, this is VA only, magnitude is VA only. So VA divided by 2. Let me change the color actually. And VC sine 60 will be somewhere around here. So it will be VC sine 60 will be root 3 divided by 2 VC. Correct. So overall, what is the resultant of this vector? So overall resultant of this vector will be this, right? Along this direction, because along this direction I have VA by 2. So resultant will be on the right hand side only. This will be VA divided by 2, and this will be root 3 by 2 VC. So I mean, this is VA only, right? Magnitude is VA only. Magnitude will not change. So this will be root 3 divided by 2 VA. Okay. Now if I find out the this value, if I find out this value, right, what will be the value? So the value here, this will be root 3 by 2 whole square plus VA by 2 whole square, that is V only. So my VBC, okay, one mistake I made, no mistake, VBC is V only. Okay, VBC is V only. Okay, VBC actually comes out to be V only. So the potential is still there. The VA potential is still there, right? So my VBC is also, even if one of the coils is open circuited, but still the VB voltage is still, VBC voltage is still VA only. Magnitude is still VA, right? Magnitude is still VA. So what can I conclude? So will the power rating be same? Because I'm getting voltage of VA. Will the power rating be same? No, the power rating won't be same. Why would the power rating won't be same? Because this time, remember, here the current is 0. So current is only present here and here. It is not actually present here, right? So what will be the actual VBC? VBC is negative of this. So VBC is negative, so it will lie somewhere around here, which is actually 120 degrees lagging from the reference VA. Because this is 60 and this overall thing will be 180, so this will be 120 only. This will be 120 only. Okay. So from here you can directly understand that basically the voltages are maintained, although this phase is open, voltages are still maintained. Okay, but this phase is open, so this phase will not be able to provide any current, so other two phases will provide the current. What is the rating? So one thing is, if it was totally connected, right, then what was the power transferred? It was root 3 VLIL. If for an open delta connection, the power or the apparent power transferred will, the expression, we are not deriving it because derivation won't be asked. This expression will come out to be this expression will come out to be VL into IL. Okay, three phase will come out to be VL into IL, because it will be 57.7% of the actual overall load. So this is in the open delta, okay, VB connection, and in power in apparent power in delta connection is root 3 into VL into IL. Okay, so this will be S delta delta divided by SVV will be equals to not delta, sorry, SVV upon S delta delta will be equals to VLIL divided by root 3 VLIL. Okay, so this will come out to be 1 by root 3 into 100% basically. So like it is basically 57.7%. Now let's understand from the circuital point of view why this will be 1 by root 3. Why is this the case? Because I know few things are not cleared. So I have drawn few circuits. Okay, so if everything is fine, if there is no open delta connection, everything is fine, right? All the coils are operating totally perfectly. Then let's assume an example. Let's take example that the coil current is 10 amperes. So what will be the line current? So phase current is 10 amperes. What will be the line current? Line current will be 17.3. Why? Because it is basically, because in delta the line current is root 3 times the phase current. This we already know, right? It is root 3 times the phase current. Okay, so that is what my line current is. It is root 3 times my phase current. So here if the phase current is 10 amperes, so line current will be 17.3 amperes. Okay, now what happens in an open delta connection? So if in an open delta connection, I'm telling you that the load is balanced and one of the phase is vanished. Okay, one of the phase is gone. If load is balanced, whatever the current here will be same across all the three phases, correct? So if this is gone, right, this is gone bad, this is open circuited, so no current is flowing through here. So whatever current is flowing through this coil, what is the maximum current that this coil can take? 10 amperes as proven here, right? So again, this current has to be same as this current because here the current is 0. So the line current also becomes 10 ampere now. Again, what I have said you load is balanced. So if load is balanced, if one of the line currents is 10 amperes, all the others also will be 10 amperes only. Phase difference will be different, like 120 degree phase apart, but this will be the line currents now. It is not a delta connection anymore. It is not a simple delta connection. So I cannot use the relationship that my line current will be equals to root 3 times phase current. I cannot use it here because it is not a delta connection. It is not a delta connection. So just be careful about that. So that's why here the line currents are 10 ampere. Now what is the power consumed? So I told you, right, the voltages do not change, the currents change. So it will be root 3 times the line voltage into the line current. So what is the line current now? Line current is the root 3 times lower than the previous line current. So previously it was IL, now it has become IL by root 3. Why? Because that is what my maximum current that the phase can support. So this is IL by root 3, right? 17.32 by root 3. So that's why this is IL by root 3. So ultimately the three phase power in open delta connection for a balanced load becomes VL into IL. It is not root 3 into VL into IL. So you see, right? You observe here, that's why here I have written that in open delta connection the power is VL into IL, and in delta delta normal operation it is root 3 VL into IL. I hope this is confused. I don't want to confuse you with phasor diagram and all those things. That is a very lengthy derivation. I don't want to go to that because that is not required. Whatever is required, whatever conceptual is required, I have told you. So in interview, if someone asks you how is it 1 by root 3 times, or how is it 57.7% of the delta delta connection, now I hope you can prove it to them. So this is how, okay, just draw the circuits and just prove it to them. So there is one more term known as transformer utilization factor. So what is transformer utilization factor? It is basically the output power by the rating of the transformer. So in this case, right, actually I am not able to utilize the transformer fully. I am not able to utilize the transformer fully. Why I am not able to utilize the transformer fully? Because what is the rating of the transformer? Here two phases are there. Two phases are there, right? Two phases are there. So the rating of the transformer is, if three phases were there, the rating of the transformer is supposed to be 3 V phase into I phase. That is the 3 phase power, right? If two phases are there, the rating of the transformer will be 2 V phase into I phase, because I am able to utilize two phases. Correct? If three phases were there, I would have been able to utilize three phases. Okay, 2 V phase into I phase. Now, what is the output power that I am getting in the load? The output power in this case, in a open delta connection, the output power I am getting is VL into IL. Already derived. Already I have derived it here. VL into IL. Now I know in delta connection V phase and I phase are same. So V phase and VL are same. So it is VL into IL divided by 2 into VL I phase. Now what is I phase? So in case of a balanced load, I know I phase is IL by root 3. I am just deriving for a balanced load. So suppose if it was a balanced load, all this is just assumption, okay? Just it is a metric, that's it. This can be asked in interview, that's why I am telling you, okay? So if it is a balance, then my I phase will be IL by root 3 in case of delta connection, but here it is not balanced. I am again telling you it is not balanced. But suppose if I assume it to be balanced, then my I phase will be IL divided by root 3. So from here I get a very beautiful expression that the transformer utilization factor is root 3. Transformer utilization factor is root 3 by 2, or it is 0.866, or it is 86.6%. So this also can be asked in other exams, like not GATE, in other exams, AEJ exams, this particular relationship can be asked. So I hope it is now cleared about the ratio of this delta delta power transfer and normal open delta transfer. Okay, so this was about the case. Now, like, why use open delta? So it can be an emergency backup. Even if one of the windings of the transformer is open, still I am able to serve the load. Okay, even if one of the delta bank fails, still the system is continuously operating. It will operate at lower loads, that is 57.7%, but still complete shutdown won't be happening. So it is very critical in very important in critical systems. Reduced cost for light loads. Okay, in some rural or lightly loaded industrial areas, initially only 2 transformers are installed in open delta to reduce cost. Okay, a third transformer can be added later when the load demand increases to convert it into a closed delta. Okay, so later we can add it so that we increase the, like, for certain cases open delta is good. Okay, initially only 2 transformers are installed, then as demand increases I install the third transformer, so initial cost will be reduced. Okay, continuity of supply as discussed here as well. Okay, Power capacity already discussed, that power capacity will be 57.7% of the three phase transformer, or simply delta delta transformer. Open delta is said as VV. Okay, remember this means each transformer is loaded more than it would be in closed delta. That means basically not each transformer, that means basically means each phase of the transformer, each coil of the transformer, each coil of the transformer. Okay, now what are the disadvantages? We are only able to serve 57.7% of the total rated capacity of these three transformers. Okay, unbalanced load handling. So poor, like although here the voltages are same, but unbalanced current can flow through the loop that can actually damage the system. Okay, losses will be more because the two windings of the transformer will carry more current, so there will be huge losses and overheating that can damage the system. And of course it is not suitable for large loads because we can only serve 57.7% of the full load. Okay, so these are the applications, you can go through this, and these are the differences between the open delta and your uh, delta delta connection. Okay, now let's start with harmonics. So what are harmonics basically? Harmonics are those kind components which are not purely sinusoidal. Harmonics are unwanted components which we don't want. So harmonics are unwanted components. Okay, harmonics are unwanted components. So what we can say is uh, that let's assume like my voltage has some value Vm sine omega t plus, let's say Vm1 sine omega t, Vm3 sine 3 omega t plus some Vm5 sine 5 omega t. Okay, these are unwanted. We will discuss more about harmonics later on as well. And the current, right? Let's say if the current is purely sinusoidal, there is no problem. But let's say current also has harmonics. Harmonics means like this is my fundamental frequency omega. This is what we want, fundamental frequency, right? This is what we want actually. But what is the problem? Problem is I'm getting harmonics. So whenever we are generating a voltage, I want to generate this value. But due to some imperfections in the construction, in the development of the voltage, of course due to practical changes, what happens, these components also get developed. And if these components develop, what happens, they induce problems in the circuit. Why? Because your circuit will consist of R, L and C, and whatever components, whatever values we have chosen here, R, L, C, that was with respect to omega frequency. But if these components are also there, the impedance will change. If the impedance changes, the circuit working might change. That is not a good factor. Although generally the magnitude or amplitude of the harmonics will be much lower. Like Vm3 will be much lower than Vm1, and Vm5 will be much lower than Vm3. Okay, it will keep on reducing as I increase my harmonics. It will keep on reducing, but still there can be effect, there can be overheating, there can be some currents, all these things can be there. Okay, power consumed due to the harmonic will also you can calculate. Like let's say this is Im1 sin omega t minus 5 plus Im3 omega 3 minus 5 plus Im5 sin 5 omega t minus 5. Okay, You can easily calculate the power, not phi, sorry, this will be some phi, this will be phi 1, this will be phi 3, this will be phi 5. Okay, so you can easily calculate the powers. So these power consumed are actually not useful power because I am not able to use it. It is getting lost in here somewhere here, right? My ultimate use is this power only. Vm1, Im1 cos phi 1. All this power actually I am not able to use. So these are also wasted power that I should have been able to utilize here. Okay, that is getting used here. Okay, so complex power I have taught you, so I am not explaining how am I calculating the power here. Okay, how does harmonic comes? So generally, right, our aim is to develop a pure sine wave, but actually we are not able to develop a pure sine wave. And if the input voltage is not pure sine wave, then if you know the transformer, right, transformer working also will not be pure sine wave, right? Transformer, how does a transformer work? Transformer, right, we differentiate the flux, then the magnetizing current is developed from, like that, right? All those things, induced voltage is developed. So if my voltage, like the input of the voltage of the transformer is not sinusoidal, so the flux will not be sinusoidal. If flux is not sinusoidal, then the induced voltage on the other side also will not be sinusoidal. So these are the problems basically. So the waveform, instead of looking like a pure sine wave, it will look like something like this. Somewhat like this, something like this. Okay, not purely sinusoidal, bit of harmonics, so it will not be pure sinusoidal. So it will be this, right, this waveform will be a combination of a pure sine wave and few other waveforms like this, high frequency, right, like this we will study in Fourier series. Okay, signals and systems. Okay, this was about the bit of introduction about harmonics. Why does harmonics come up? Okay, now let's go through a few things here. uh, so mainly, right, we will conclude the main things which are required. Actually, we'll just do the conclusions which are required. Okay, so remember, how in transformer how harmonics can come. So there are many ways with which how harmonics can come. If my input V in is not purely sinusoidal, not purely sinusoidal. Okay, if the input is not purely sinusoidal, and other way, my core can saturate, right? If core saturates, then also the induced voltage will contain harmonics. If my flux is not purely sinusoidal, flux, why is flux not purely sinusoidal? There can be many reasons. There can be many reasons, like if my BH curve is non-linear. If my BH curve is non-linear, then for a sinusoidal current, the flux will not be sinusoidal because it is non-linear. We will see this. Okay, so these are the few phenomena due to which the flux, right, can be non-sinusoidal. If the flux is non-sinusoidal, the induced EMF will be non-sinusoidal. If the induced EMF is non-sinusoidal, output voltage will not be sinusoidal. There can be problems. Okay, so let's start with the first case. In the first case, mainly we will discuss about the magnetizing current. Okay, just keep in mind whatever I am discussing, that you need to keep in mind. Everything else no need to study. Okay, case 1, core with linear BH characteristics. So if I have a core that is linear BH characteristics, that means if I increase B, H also will increase in the same proportionality. So my phi t is this value. Okay, phi t is this value. It is, assumption is phi t is purely sinusoidal. So if phi t is purely sinusoidal, right, my flux also will be, sorry, my current also will be purely sinusoidal, right? So if my applied voltage is purely sinusoidal, then basically then the core flux should also be purely sinusoidal. Then the magnetizing curve, sorry, uh, then the magnetizing current also will be purely sinusoidal. So everything here is satisfying. Basically, what it means is, if I am applying a sinusoidal voltage, I know what is it. So voltage is equals to like it is proportional to d phi by dt. Okay, and I know like if voltage is sinusoidal, it will be co-sinusoidal, so almost it is sinusoidal only, it is sinusoidal only. Okay, so what I can comment, is that if my BH curve is linear and if my flux is sinusoidal, then my current also will be sinusoidal. This is the first what do you say, conclusion. So I will write here, if BH curve is linear and my V in input voltage is linear, that means my core flux will be linear. Okay, and the basically what do you say, the magnetizing current, then the conclusion is magnetizing current Im also will be sinusoidal, it will be sine function. Okay, it will be purely sinusoidal, pure sine. So now let's discuss about the type of core where the core will saturate. So if the core saturates, now what will happen? If the core saturates, one thing I will notice is here, right, core was linear. If core was linear, then whatever the change in flux there was, it was totally reflecting in the magnetizing current. But as the core is saturating, now I will discuss about slope. So here, right, if I observe, here I have some slope. Here let's write this slope as let me color this as this slope and this slope. So here, right, the slope is what? Slope is basically dB upon dH. I know B is proportional to flux, so basically it is d phi upon dH, d phi upon di, right? Because magnetizing force is proportional to current, magnetic flux density is proportional to flux. Okay, so what I can comment is d phi by di is proportional, right? Here, right, the slope is higher, right? Slope is more here, so it is more, let's say case 1 than this case, right? That is d phi 2 by di2. What does it actually mean? What does this represent? Mathematically, this means that if there is some change in d phi, there will be very less change in di. Why? Because this is larger. So if let's say the numerator is constant for both of these cases, I am observing for the same change in d phi. If the numerator is constant, that means this is larger, this quantity is larger, that means the denominator has to be smaller. So that means change in current has to be smaller. So initially the change in current will be not that high. Okay, so change in current will be not that high. So initially the current graph will be somewhat like this. Okay, suddenly as I will move along the BH curve, what will happen here, the d phi 2 upon di2, right, it is smaller than the previous one. So for the same change in flux, as it is smaller, the denominator has to be more, right, higher than this. So the change in current will be larger, so suddenly there will be spikes in the current, right? Simple slope concept I have used, because the slope here is larger, so change in flux, if I assume that change in flux is same, so as the slope is larger, denominator has to be smaller, so change in current will be smaller. Okay, here if the change in flux, here also change in flux is same, again slope is smaller here. If the slope is smaller, that means the change in current will be larger. This whole thing is smaller, so the numerator is constant, so denominator has to be larger. Okay, so that's why the nature of the current curve will come something like this. This nature is called as peaky magnetizing current. Peaky magnetizing current. Okay, and this happens when peaky magnetizing current. So peaky magnetizing current happens when assumption is your input voltage is sinusoidal. Okay, assumption is your input voltage is sinusoidal. but your flux is also sinusoidal, your phi of t is also sinusoidal, but your core is non-linear or it saturates. Core is non-linear and it saturates. Core is non-linear and it saturates. Okay, so what I can comment, then the conclusion will be, that the magnetizing current will be magnetizing current will be what do you say, magnetizing current will be peaky in nature. Now you might have a doubt, sir, if the magnetizing current is peaky in nature, I know that due to magnetizing current only flux get developed. Okay, so flux also will be peaky in nature. You are kind of correct, okay. Actually what happens in reality, practically, so I will write here practically, right? Practically, if the magnetizing current Im contains harmonic, then of course phi m also will contain harmonic, right? Phi of t also will contain harmonic, contain harmonic. But ideally, like, we are actually studying everything ideal and in questions, right, if it is mentioned, but for solving questions, whatever we have discussed, you will use that concept only for solving questions. You will use the above concepts. Okay, that's it basically. So here, right, the current waveform is peaky in nature. So can I draw the current waveform, what kind of harmonics it will contain? So current waveform is peaking in nature. Okay, so current waveform is peaking in nature like this, right? So this is a combination of a sinusoidal actually. So let's assume my sinusoidal is somewhat like this. So what will be the other components? So other components, right, will be somewhat like this. Okay, other components will be somewhat like this. This will be one of the components. So here if you see that during this place it is negative, this is positive, so the superimpose of this will be somewhat like this, and both are positive in this particular region. So that's why this, right, actually sorry my graph is wrong. This, right, this should be here. Yeah, not perfectly sinusoidal, but I hope you understand the point. So here, right, both during this point both are superimposing, so both will be added, and here, right, both will not be added. Okay, so yeah, that is the case over here. Okay, so yeah, I hope you have understood this basic point, right? So that's how the harmonics are developed. So here it was actually supposed to be a pure sine wave, but current waveform is peaky in nature, so I see a third harmonic. Why it is a third harmonic? If I see in one half cycle, this is covering 3 cycles, right? Sorry, not in 1/2 cycle. Yeah, 1/2 cycle only. In 1/2 cycle, it is covering 1.5 cycle. Okay, let me complete the whole cycle, then you will understand this better. So in a whole cycle, how many cycles is this green waveform covering? So the green waveform is actually covering total, in a whole cycle, the green waveform is covering 3 cycles, right? 3 cycles of sine. So that means if the blue waveform has a frequency of omega, the green waveform will have a frequency of 3 omega. Very simple, right? Because the time period has reduced by 3. Okay, so that's how the third harmonic gets developed mostly, right? The third harmonic is the dominant component. Okay, so uh, so here, right, in this case, third harmonic current flows. So in this case, I see third harmonic current. So this is third harmonic current. Okay, so one more thing we have to keep in mind, that third harmonic current and zero sequence current are kind of same. What do I mean by it? Okay, what do I mean by third harmonic current and zero sequence current? Okay, so let's discuss about this third harmonic current, right? So what are third harmonics? So basically third harmonics means the frequency will be 3 times the actual frequency. So for phase A, my value was IM1, right? I1M. Okay, let me increase it. I1M, like my fundamental component of the current, magnetizing current, was I1M sine omega t, right? Because it has no phase shift, 0. The phase B component will be I1M sine omega t minus 120, and the phase C component will be I1M sine omega t plus 120 degrees. Okay, now what can I say about the third harmonics? Third harmonics will be just 3 times multiplied by this, right? Whatever the value is inside there, 3 times multiplied by this. Correct? 3 times multiplied by this, because like it is just thrice the frequency. So for sine omega t, it will be like this. For other right, it will be 3 times multiplied for the other phases. So if I multiply by 3, I observe I am getting this expression, right? If I observe anything very closely, this, right, this is actually I3M sine of 3 omega t. If I take the 3 inside, minus 360, and this is basically I 3M sine of 3 omega t plus 360. Okay, so that basically means that there is no phase difference at all between the third harmonic currents. There is no phase difference, so all of them are in the same phase. So this is my phase A, this is my phase B, this is my phase C, right? For third harmonic, I'm specifically talking about third harmonic. So all the third harmonic currents are in the same phase. That means they are also called as zero sequence components. This we will study in the PSA, power system analysis. Zero sequence means that there is no phase difference. So V angle 0, V1 angle 0, V2 angle 0, okay, V3 angle 0. Basically they are constant values. These are constant values, right? There is no phase shift. These are constant values, like in magnitude terms. Okay, also they are called as co-phased. Okay, same phased or co-phased. Sometimes they are called as same phased or co-phased. Same phased or co-phased. Okay, so this was about the third harmonic. So third harmonic can come in two ways. If my waveform nature is peaky, So third harmonic will come something like this. If my waveform nature is like this, so during the middle it is lower and during the other ends it is higher, so third harmonic will be like this. Okay, but third harmonic will be present and it will be the most dominating value. It will be the most dominating value. That is one key thing that you should keep in mind. Okay, I hope you have understood this point. So there are other kind of other components as well. Zero sequence components, then there is positive sequence components. Positive sequence means ABC, whatever is the sequence of the supply, same sequence, and negative sequence means opposite of the supply, opposite sequence of the supply. Okay, got it? Okay, so we have learned about third harmonics a bit. Now let's come to the case 3, and in the case 3 where my current my magnetizing current is sinusoidal. Okay, so my IM is sinusoidal. For that, what kind of flux I will get? So we cannot actually analyze two things, both the flux and the current at once, right? We assume one thing to be ideal and we try to develop the intuition for the other component. Practically, as I mentioned here, practically if Im contains harmonic, phi m also will contain harmonic. If phi m contains harmonic, Im also will contain harmonic, right? It is not possible. It is not possible, right? But ideally, if I assume that my magnetizing current is purely sinusoidal and my the core is again non-linear core with saturation, then what will happen? Then what kind of flux waveform I will get? So again, if I see, if I do the same analysis, right here, right, in this particular region, that in this particular region my current is okay. So if my like my current is increasing, so is my flux is increasing. So it will behave slightly like a sinusoidal, not exactly because it is non-linear, slightly like sinusoidal. But as soon as I reach at this point, what happens? If my current increases, right, the flux will not increase because the core has saturated. So flux will not increase. Any increase in current will not increase any flux. So core will be saturated. Then again, as soon as I reduce my current after this level, then again the flux will reduce, and like this it will happen in the other side as well. Correct? So basically here the waveform that I am getting is a flat topped waveform. It is a flat topped waveform. So if it is a flat top waveform, that means what? My induced EMF also will be non-sinusoidal because flux is non-sinusoidal and my induced EMF E induced is basically proportional to d phi by dt, right? So if of course the flux is not sinusoidal, my induced EMF will not be sinusoidal. Conclusion is, if my magnetizing current is sinusoidal, core is non-linear, then the induced EMF will be non-sinusoidal. Previously what we discussed, if my flux is sinusoidal, core is non-linear, then my magnetizing current will be peaky in nature. Magnetizing current will be peaky in nature. In this case, my induced EMF will be sinusoidal though. Induced EMF will be sinusoidal, okay? Because flux is sinusoidal. Same here, right? Induced EMF, not here actually, here, right? As the flux is non-sinusoidal, so induced EMF will be non-sinusoidal. As simple as that. So these are the main conclusions that you need to keep in mind. Okay, and how will I get this flat top waveform? Like this here, right? Here if you see, here, right, here it is like a flat top waveform. So this is like a flat top waveform where the third harmonic is like this, and here the third harmonic is just opposite. So this is like a peaky waveform. So this is a flat top waveform, and this is a peaky waveform. Okay, so these are the things that you need to keep in mind basically. Okay, so basically here my induced EMF, the point is my induced EMF will contain third harmonic voltages. Okay, induced EMF will contain third harmonic voltages. Okay, which becomes peaky in nature and contains dominant third harmonic. One more thing is that how when my induced EMF, like, yeah, my induced EMF will be non-sinusoidal, but will my induced EMF also will be flat top? No, my induced EMF is the differentiation of the flux. So here if I see, if I differentiate this waveform, how, what will the differentiation look like? So if I draw the waveform here, if I draw the waveform here, right, waveform of flux. So if I draw the waveform of flux, waveform of flux. So waveform of flux, right? Here it will be proportional to the differentiation. So here the differentiation is almost like linear. It is like almost sinusoidal only. It will be almost like sinusoidal. But here if I see, there is very large change in flux, right? Here, right, there is very less change in flux. So here there is, I mean, the flux is changing constantly. So there is very less change. Actually, what is happening? The waveform is somewhat like this, right? Waveform is somewhat like this. Suddenly it is becoming flat top. So phi of t is made of two components. One will be the pure component, that is this one. Another one will be the third harmonic component, right? Third harmonic component is this one. It is, I guess, it will be this one. Okay. So this is my third harmonic component, phi 3 of t, and this is my fundamental component, phi 1 of t. Okay, third harmonic component and fundamental component. Okay, so this, right, this will be what I can comment. What I can comment here is what will be the induced EMF. So the induced EMF due to phi 1 of t will be what? Induced EMF due to phi 1 of t will be E1 of t, and the induced EMF due to this will be what? This is a sinusoidal. Okay, it will be like a like differentiation of this will be cosinusoidal. Sorry, the differentiation of this will be what? Differentiation of this will be cosinusoid, right? This is a sine function. Differentiation will be cosinusoid. And how does the cosinusoid start? Cosinusoid is 0 at pi by 2. So the differentiation will be here. E1 will be something like this. Okay, roughly. So basically, as this is a sine function, the differentiation will be a cosine. So at pi by 2, the value will be 0. At pi by 2, the value will be 0. Okay. Now, what about this third harmonic? So again, it is a sine. So differentiation will be a cosine. So cosine will be somewhat like this, right? Cosine will be somewhat like this. It will start with a lag. Correct? If I am not mistaken, it will start with a lag. Okay, so here, right, now if I superimpose, so this is the third induced EMF due to the third harmonic, this is the induced EMF due to the fundamental component. So if I add these two, what I am observing, that here, right, this is reducing. So in this region, the value of flux, value of induced EMF is reducing. Here as well, the value of induced EMF is reducing, because this is negative, this is positive. This is positive between this region, and this is also positive. So actually my overall induced EMF, if I draw as a whole, so initially it is somewhat negative, not negative, sorry, initially it is like this 0, and then whenever this is positive, right, the third harmonic is positive, then this becomes positive, peaky in nature. So basically if my this is the resultant EMF, induced EMF. So what is the conclusion? Conclusion is if my flux is flat topped, my induced EMF will be peaky in nature. Okay, here if my magnetizing current is peaky in nature, then my flux was sinusoidal and my induced EMF also was sinusoidal. Here if my magnetic flux is flat top, that is my current is purely sinusoidal, hence my induced EMF induced EMF will be peaky in nature. Okay, these are the main things that you need to keep in mind. Okay, but remember, all these are theoretical points. Practically both will contain harmonics, the induced both the flux and the magnetizing current, right? I'm saying it over and over again. Okay, now what will happen to the core loss and the your what will happen to the hysteresis loss and the eddy current loss, basically the core losses. Okay, so uh, the core loss will actually increase. Why will the core loss increase? Why will the core loss increase? We will discuss about this, how the core loss will increase. So I know that my uh, harmonic, my induced EMF will contain harmonics, right? Induced EMF will contain harmonics because my flux has harmonics. So flux phi of t will be phi m1 of sin omega t, omega t plus phi m2 phi m3 sin 3 omega t plus phi m5 sin 5 omega t, and so on. So what will be the induced EMF? Induced EMF, right? E of t will be what? N d phi dt, right? N d phi dt. Whichever side I am in, either in secondary or primary, it does not matter. Okay. N d phi dt. So this will be N into ddt. So flux is this value. So this will be ddt of differentiation of this will be phi m1 omega cos of omega t plus phi m3 3 omega cos of some 3 omega t, and so on, right? It will go on. So what I observe is basically what will be the flux, right, or induced EMF for the third and the, I mean for the third harmonic and the first fundamental component. So what is the third harmonic component among the fundamental component? It will be basically phi 3 omega into phi m3, like I'm just talking about the peak value max. Okay, E3 max and the E1 max, right? This can be asked in a question. That is what am I solving this, right? This kind of things can be asked in a question. Okay, they can make a question out of this. This will be 3 omega phi m3 divided by omega phi m1. Okay, so this will be 3 phi m3 divided by phi m1. Okay, so this can be asked in a question. This can be asked, right? If the peak flux density, like peak flux or density is also given, this can be also converted in terms of peak flux density. So these kind of questions can be asked. Okay, this will be bm3 upon bm1. Okay, so they will ask you the ratio of the third harmonic, peak value of the third harmonic voltage upon the peak value of the fundamental component. Also they can ask you RMS, ratio of RMS as well, because I will just divide this by root 2 and that will give me the RMS value. Does not make any difference. Now what will happen to the what do you say, what will happen to the losses, core losses basically. So I know what are my core losses. If you remember, my core losses were equals to the eddy current loss, that is Ke, eddy current constant, it is proportional to F square and Bm square. Volume is there, that is already inbuilt of Ke, because volume is constant, that is already inbuilt of Ke, plus Kh, the hysteresis constant, into F, it is actually F, it is like directly proportional to the frequency, and Bm raised to power x, where x is the Steinmetz constant, right? X is a Steinmetz constant. So in different frequencies, right, the peak flux density will also change. It will be phi m1, phi m2. So what I can write here, the overall loss, let's say, will be divided into eddy current loss and the hysteresis loss. So eddy current loss will be Ke, right? This Ke will be constant only. K will be constant. First, it will be due to the fundamental component, so F square into Bm square, Bm1 square, fundamental component. Then it will be Ke into 3F square due to the third harmonic component, 3F whole square, 3F whole square into Bm, Bm3 whole square, plus Ke into 5F whole square into plus into Bm 5 whole square. Okay, and so on, right? So on. Here as well the same thing, only my hysteresis loss. So my hysteresis loss will be equals to Ke Kh F into Bm1 x plus Kh into 3F into Bm3 raised to power x, and so on, right? So my like this calculation can come, this kind of question can come, and overall core loss Pc will be basically the sum of the hysteresis, overall hysteresis, and the eddy current loss. Okay, that's why we say that if I have harmonics, you see the core loss increases, so more the core becomes more hotter. So this is a disadvantage. That's why we say harmonics are unwanted. Okay, so I will write here, as we observe, as we observe that with harmonics, core loss increases. Core loss increases. So uh, uh, what can I say is there will be more heating of the core, more heating. Of course. So that's why these are unwanted. So now let's discuss about the next thing, that is magnetizing inrush current. What is magnetizing inrush current? We know that our flux, right, our voltage, induced EMF voltage V of t is d phi by dt. Okay, but what if I want to derive flux, right? Because like the induced EMF will be minus n d phi dt, right? It is minus n d phi dt. Okay, what about the flux? If let's say I am applying a voltage, what will be the flux value? I will integrate on both sides, so it will be phi of t phi of t will be equals to basically minus of 1 by n integration of v of t dt. Okay, so let's analyze two cases. What are the two cases? So let's analyze for a case where I am starting at omega t equal to 0. So I am starting when my voltage is 0, and in the second case I am starting when my voltage is peak value Vm. Okay, I have closed this switch at omega t equals to 0 and at omega t equals to pi by 2. So this value is pi by 2 when the voltage waveform is peak, input voltage waveform is peak. So if I start from here, right, it is simply like, ignore the negative sign for now, ignore the negative sign for now, it is simply integration of v of t. So here, right, the area is increasing, like it is area of v of t from 0 to t. So in this whole region the area is increasing only, area is never decreasing, right, area is always increasing. So what will happen is area will keep on increasing, right, area will keep on increasing like this. Okay, although it will be like a cos function only. Okay, because I'm integrating this. Yeah, look, I will discuss about that. Let's assume that initially the flux was 0. If initially the flux was 0, area will keep on increasing, and until this point, after this what happens, my voltage is negative, so area is in the negative area, so positive area is already here, I am subtracting smaller negative area, so the flux will reduce. Basically flux will reduce, and ultimately what will happen, it will never go to 0, it will go to 0 again here, and this will be the flux waveform like this. Okay, roughly. Okay, not exactly like this, roughly I'm talking about. This is not the actual flux waveform, I'm just talking, I'm giving you the feeling. Okay, now what happens, this, right, goes from 0, starts from 0, and this goes to some very high value. I don't know what is the high value, this goes to some high value. Okay, here, what if I would have done the same thing in pi by 2? What if my switch was closed in pi by 2? If my switch was closed in pi by 2, then what will happen? If my switch was closed in pi by 2, then from here my zero flux, like initially I have zero flux, so again I encounter a positive area, so positive area, positive area, positive area, until pi positive area. That's why the flux value increases, right, because I'm just integrating the area, I'm just adding up the areas. Here again the value is negative. If the value is negative, that means overall flux will reduce, right, overall flux will reduce, phi of t will reduce. So this flux will reduce, this flux will reduce, this flux will reduce, this flux will reduce, this flux will be here. Okay, this flux will be here, and again it will reduce more further, right, because I have more negative area. So this region actually where the negative area and the positive area cancels each other out, that's why it is 0. Again the negative area is more, so it will go like this and it will go on, right. What is the problem here? Like basically, right, there is no problem, like because at steady state the waveform will look something like this only. Steady state, right, steady state the waveform will be something like this only, because I am basically integrating a sine function. If I am integrating a sine function, I will get a cos. If I am integrating a sine function, I will get a cos. Okay, so this is more like a cos, this is not like a cos, right. So this is just the transient one. For 1-2 cycles this will happen. What does it mean? So for 1-2 cycles, right, the positive area will be more than the negative area. So hence basically only at this point both the positive area and negative area is equal, otherwise the positive area is always higher than the negative area at all points. So here, right, the flux is more in first few cycles, in the next few cycles automatically it will be okay. In steady state automatically it will be okay, it will be like a cosinusoid only. Just in transient the flux is more, so phi m is more in transient, phi m is more in transient. If phi m is more in transient, that means what? That means there is a probability, there is a probability of core getting saturated, of core getting saturated. Okay, understood. So that's why if the phi m is more, phi m is more means what? Phi m more means I need more magnetizing current. So that's why initially in transient there is a magnetic inrush current. This is known as the magnetic inrush current due to the time of the switching. If you remember, if you have studied AC transient, you will know this concept, because what is the voltage expression or the current expression on the circuit depends of the time of switching, that is the theta. I hope you remember the AC transient, okay, which Himanshu has taught. So same thing is here. During the first few cases, what will happen? There will be bit of transient. Due to that, the flux will be more. If flux is more, magnetizing current is more. That means initially a huge magnetizing current will flow. That is what is mentioned over here. Okay. So if the switch is closed at omega t equals to pi by 2, then there is no problem. If it is closed at omega t equal to 0, then there is problem. Flux is higher, it goes beyond saturation, can go beyond saturation. To establish this flux, the transformer draws large non-sinusoidal magnetizing current, because after saturation the current is non-sinusoidal only, because we are after saturation, BH curve in the saturation region, right? That's why the magnetizing current will be non-sinusoidal. Harmonics will be there, magnetizing current also will be higher. Okay, so all these are the problems. So this is the phenomenon known as the inrush current. So mainly these are few theoretical points that you should keep in mind. So this is called as the inrush current or the magnetic inrush current. Okay. So I hope you have understood this basic point. So this is a summary. So what is the characteristics of inrush currents? It will be high amplitude, 6 to 10 times of the rated magnetizing current. Basically whatever is the rated magnetizing current, not the rated overall winding current. It is reached in second harmonics and typically lasts for first few cycles. After that, obviously it will die down, just like transient only last for first initial phases, then automatically we reach the steady state. Okay, so we have few protection like mechanisms, you can go through this. Okay, summary, whatever we have learned till now is that for linear BH curve, and if the flux is sinusoidal, magnetizing current also will be sinusoidal. There will not be any harmonics. It will be totally ideal condition, but of course we don't live in ideal life, right? So if the core is saturated, then there will be zero sequence currents. If the flux is sinusoidal, then the magnetizing current will have zero sequence components, that is third harmonic components. Magnetizing current will be peaky in nature. My magnetizing current will contain third harmonics, okay, and its induced EMF, in this case the E induced also will be sinusoidal, because the flux is sinusoidal. E induced will be sinusoidal, okay, and it is generally found in single phase and delta connected winding. We will discuss about three phase in the next slides. Okay, next, if the core is saturated again, but this time the magnetizing current is sinusoidal. If the magnetizing current is sinusoidal, then my flux will be flattened, that is also known as flat topped, and my EMF will be peaky in nature. Both will contain third harmonics. My magnetizing current will not contain any harmonics. Okay, so yeah, these are basically few things. We will discuss about the star, all those things in the next slides. So now let's quickly summarize whatever we have learned. So one thing is for sure, that what is the key takeaway? The key takeaway is that if the exciting or the magnetizing current is assumed to be purely sinusoidal, that is at 50 Hz, then the resulting flux in the transformer core will have harmonics, and mainly the third harmonic will be the dominating. Of course there will be other harmonics like fifth harmonic, seventh harmonic, those will be there, but I will show you that the most dominating harmonic will be the third harmonic. Just believe on me. If you like go and solve in signals and system, you will see as the order of harmonic becomes higher, the amplitude becomes lower and lower, so the effect also becomes lower and lower. So the third harmonic mostly is the most dominating one, and our main focus will be to reduce this third harmonic. Okay, now conversely, if I say, if in the transformer core I have a purely sinusoidal flux, then the exciting current or the magnetizing current will contain both the fundamental component and the third harmonic component. Okay, so both cases there will be harmonics, but in practically what happens, practically I have already concluded, practically what happens is, practically practically the current Im and phi m both contain harmonics practically, but ideally we will do our analysis according to this conclusion. This is the conclusion, right? According to this conclusion we will do our analysis and solve questions, but practically both Im and phi m will contain harmonics. Okay, so yeah, that is the case over here. I hope you have understood this very uh, basic point. Okay, so now let's discuss about uh, what happens. So this is the conclusion I am showing you at the starting. I will prove each and everything. So for a single phase transformer, the harmonics can flow easily, right? We have already discussed that if the current is purely sinusoidal, flux will contain harmonics. If the flux is purely sinusoidal, current will contain harmonics, right? We have already discussed. Whatever analysis we are doing, we were doing for the single phase transformer. So that's why another reason to use three phase transformer is to three phase transformer can actually help reduce this harmonics, can actually help suppress the harmonics. So in three phase star star connection without any neutral, there will be no path for the zero sequence current. How? I will show you. Don't worry, I will show you. Okay, we will see this. And for star delta delta star, the delta windings offer a closed path for the circulating current, but there is no zero sequence current on the lines. So in the lines there will not be any current, only in the phases there will be current. I will prove it to you. All these things I will prove it to you. Okay, so I will show you. So the advantage for star delta or delta star transformers is that even though there is harmonics in the current, right? So even though the magnetizing current is non-sinusoidal, that means there is harmonics, the flux will remain sinusoidal, because that is what we prove, right? If the current is non-sinusoidal, flux will be sinusoidal. So what is the advantage in delta is that delta in the line there is no harmonics. In the line current there is no harmonics. I will prove it to you. But in the phases there will be harmonics. There will be a zero sequence circulating current in the phases. I will show you. Don't worry, I will show you. So just believe for a second now. So zero sequence circulating current will be there basically in this loop. Okay, there will be zero sequence circulating current in this loop, right? This will be the zero sequence circulating current, but in the lines there will not be any current. So actually the load will not see any harmonics, but in the phase there will be harmonics, and due to that harmonics the flux will be purely, not that, okay, not that, flux will be purely sinusoidal. Please don't get mistaken if I sometimes say flux instead of something else. Okay, so flux will be purely sinusoidal. So that is the advantage, and that's why in most cases you will see we use star delta transformer. Star we use because our generator is generally connected in star with a neutral, so we need the neutral, and delta is used for transmitting, right, to the transmission line. So yeah, that is the case over here basically. So like I'm just giving you a overview why we will use all these things, right? I'm just giving you a overview. Okay, okay. So yeah, now let's come to the first one. Okay, about this one, the star star connection. So what happens in a star connection? So in a star connection, the voltages, line voltages, there will not be any harmonic. In the line voltages there will not be any harmonics. Why will there not be any harmonics? So let's assume that the induced phase voltages, whatever the voltages are getting induced in the phase, let's assume it contains harmonic. So my VA will be a combination of the fundamental component and the harmonic component. So VA will be VA1 plus VA3. Then VB will be VB1 plus VB3. Okay, so what is the line voltage? What is the line voltage? These are the phase induced voltage. So if I see the line voltage VAB will be VB minus VA, right? So it will be VB minus VA. So this will be VB1 VB3 minus V1 plus Va3. Now the interesting fact is we have already discussed this, right? What we have discussed. So I hope we have discussed about zero sequence components. So where is the zero sequence component? I guess we have discussed, right? Where is it? 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 Okay, have we not discussed about zero sequence? Okay, sorry, we have not discussed about zero sequence component. Okay, I will discuss about zero sequence component. Third harmonic currents are there. Yeah, here, right, we have discussed. So here if you see that basically what happens, I have told you here, right? So all of them have zero phase and they are in equal magnitude, because previously also they were anyways in equal magnitude only. Previously also they were in equal magnitude only. So I1m is equals to I1, these are same only, right? These values are same only, just previously they were phase shifted. What I am talking about, so previously if you see my fundamental components, so if one voltage was Vm sin omega t, the other voltage was Vm sin omega t minus 120, and the third voltage was Vm sin omega t plus 120. Okay, so I observe the magnitude are same but phase is different. But in case of a third harmonic, that is third harmonic, what happens, the phase also becomes same only, because this is plus 360 minus 360, adding and subtracting 360 does not make any difference. We rotate a full circle, so that's why their phase shift is zero and their magnitude also again are same, because the peak amplitude will be same only. So that property I will use here. So I will write here that one thing for third harmonics, right? Note for third harmonics, that the third harmonics in three different phases third harmonic in three different phases will be phase shifted, will all be in same phase and equal magnitude. So yeah, sorry, a few guys are texting. So here, right, yeah, what I was discussing. So here, right, I know, hence as this is not, sorry, this is again, as I know that the third harmonic are in zero phase and equal magnitude, so I can write here like this. I can write this V B3 VB 1 minus VA1 minus this VV3 minus VA3. So I know that VB3 and VA3 are VB3 and VA3 are in same phase, equal magnitude. So they will simply cancel each other out. So I will be left with VB1 minus VA1, which is VAB. So there is actually no third harmonic component in the line. So for a star connection, the line voltages will never contain third harmonics. That is written over here. So in star connected system, even if induced phase voltages contain triplet harmonics, the line will never contain triplet harmonics, because the line in star is the difference of two phase voltages. Since triplet voltages are in phase across all three phases, their contribution cancels out when subtracting one from the other. Okay, so that is what my VAB is. VA is equals to VAB is equals to VA minus VB. So triplet components cancel out. Okay, so I hope it is clear, right? I hope it is clear. So yeah, so phase voltages on both primary and secondary sides get distorted due to the presence of 150 hertz component. So like even though the phase voltages will get distorted in case of star connection, but the line voltages will be less affected. Okay, so this is why in the star connection the line voltages appear more in star. But now let's discuss about current, right? We have discussed about phase voltage. Now let's discuss about the current. So if let's assume that the neutral is not grounded, if the neutral is not grounded, and let's assume hypothetically, let's assume that there is zero sequence current flowing through all the three phases, because there is what do you say, there is induced voltage that is that contains harmonic. So there will be currents as well. Let's assume there is a magnetizing current that has zero sequence component. That means that has this third harmonic component. So if it has third harmonic component, so all the three phases will carry, let's assume, a current of I3M. So if the neutral is not connected, and if I apply KCL at this node O, what will be the KCL? I will write IM, I3M plus I3M plus I3M equals to 0. Hence, I can safely write that 3IM, 3I3M equals to 0. Hence, I can write that I3M equals to 0. So actually third harmonic currents are not possible in the system. Third harmonic currents are not possible in the coils, right? In the coils. Okay. In case of star connection, if the neutral is not connected, so if neutral is not grounded, then triplet currents have no return path to flow. So if I use, so in case of a ungrounded star connection, there will not be any third harmonic current. If there is no third harmonic current, the flux will not be purely sinusoidal. So that is a drawback for star connection. For start to star connection, I mean for start to star connection. For start to star connection, this is a drawback, right? Flux will not be purely sinusoidal. Okay, so yeah, what happens when supply is applied? So the transformer draws a magnetizing current to establish the core flux. Our objective is to create a purely 50 hertz flux in the core to avoid distortion in the output voltage. In floating neutral star to star configuration, third harmonic currents cannot flow, as we have discussed. So if third harmonic currents cannot flow, then only the 50 hertz component of the current can flow in the line. The third harmonic exciting current is suppressed, hence the flux will not be purely sinusoidal. Whatever flux we will develop will not be sinusoidal. Okay, got it, understood, great. So here same thing is written over here. Because the transformer can only carry 50 hertz, the resulting flux will be contain both components, third harmonic component and the fundamental component. That is a bad thing, right? So if the flux, right, contains third harmonic component, so if the flux has both phi 1 plus, let's say, phi 1m plus the third harmonic component, right, phi 3m, it has both the phi 1m and phi 3m, right? So the induced voltage also will contain third harmonic, right? So induced voltage will be containing E will be equals to E3m. That's why we discussed, right? The induced voltage will always contain third harmonic components. and it can actually be a large number. The third harmonic I'm talking about, because what is the problem? Problem is, how does the induced voltage come up? So induced voltage is E equals to N d phi by dt, right? It is N d phi by dt, correct? So if I differentiate somehow the flux, it will be like the peak value phi 3m into 3. Why? Because if you remember, your flux, the third harmonic component phi 3 will be equals to basically phi 3m. I mean, I am just discussing about the third harmonic component. If I am just discussing about the third harmonic component, phi 3m will be phi 3m sine 3 omega t, right? That is the third harmonic component, correct? So if I differentiate it, so basically your 3 omega will come at the front. So if I differentiate with respect to time, so it will get multiplied, right? So there will be a factor of 3. So due to that, the like third harmonic component can be significant, 3 times that. So what is the problem here? The problem actually is not about that, okay, in the line there will not be a third harmonic component. That is not the problem. That is not the problem, right? We discussed in the line voltage there will not be any third harmonic component. So the load will not feel any third harmonic components. That is sorted. What is the problem? The problem is this case. So let's assume a case. If I assume a case that if my voltage here is V1m root 2, like the peak value of the fundamental component is root 2 times the 220 volts. 220 volts is the RMS. Okay, and let's assume a case that in case of third harmonic component, that it is 40%, the RMS is the 40% of the previous value, the flux is the 40% of the previous value. So it is 40%, so I will multiply 0.4, but remember there is a factor of 3 here, right? There is a factor of 3, so I have to multiply 3 also. So 40% is the peak flux. So what does this 40% mean? So this 40% means that the third harmonic component, you will observe in Fourier series when you will derive that the as the order of the harmonics increases, the peak value reduces by a factor of n, by a factor of the order. So let's assume that the third harmonic flux, right, peak value of the third harmonic flux is 40% of the fundamental component. But now I'm differentiating it, right, because I have to find out the induced voltage. So if I'm differentiating it, here you see a factor of 3 comes up, right? All other factors will be common, omega, phi 3m, phi, those will be common. Just this extra factor 3 will come up, okay? Just small calculation. So if this extra factor 3 comes up, what is the problem? So this will be 1.2 times the previous peak value. So it becomes 373.35. What is the problem? So the third harmonic has higher peak value. So we know one thing, that the insulation of any device is derived from the peak value. Whatever the peak value, peak voltage will come across that device. So the peak voltage increases. So here the peak voltage increases. Peak voltage increases. Okay, okay, that is the case over here. So there can be chances of insulation breakdown or failure. So that's why we generally tend to avoid star-star connection, because the peak value of the voltage can increase. So that is a bad like disadvantage of this star connection ungrounded. Now how to solve this? We can simply connect the neutral. So now if I connect the neutral and again do the same analysis and again assume that if there is some currents flowing through the transformer, right? If there is some currents flowing through the transformer, what will happen? Okay, so here let's assume that there is some current. Let me take a pen. This, let's assume this is some current I3m. This is another current I3m. This is another current I3m. Okay, so So yeah, so now if I write the KCL, is the KCL violating now? KCL will be valid because I will assume a current here I Ix. I will assume a current here Ix. Okay. So now if I apply the KCL, it will be Ix will be equals to I3M plus I3M plus I3M. Okay. So this will be equals to 3 I3M. So Ix will be equals to 3 I3M. So in this case, if the neutral is grounded, third harmonic currents will flow. Okay. In this case, third harmonic current will flow. But what about some other case? If I want to discuss about a other case, so for the other case, right, I have to just hold on. I have to bring this front here. Yeah, one more disadvantage is there. Yeah, this one is not actually. Yeah, this one is the problem. So here, right, will third harmonic currents? Okay, sorry. Here, will the third harmonic currents flow? No, right? Third harmonic currents will not flow here. Why? Because even though here the KCL is validating that yes, third harmonic currents can flow, but here, right, there is no place for the third harmonic current to flow. Here there is no place for the third harmonic current to flow, right? So here, right, induced EMF will contain harmonic in both the primary and secondary in this case, because here this point neutral is grounded, but this point neutral is not grounded. So here, right, what will happen? What will happen that in this case, even though the neutral is grounded, but only for one of the side. Let's assume this is the primary or this is the secondary, like that, right? Whatever. If I assume this to be a transformer only, okay, okay. Or let's assume if the primary of the transformer is not grounded, but the secondary of the neutral is grounded, right? So here what will happen is that induced EMF induced EMF induced EMF in this case will contain harmonic in both primary and secondary. And in this case, it is also called as the case of floating neutral. So in this case, neutral point will be floating. Okay, or also called as oscillating, floating or oscillating. Why it will be oscillating? Because here, right, it will not be purely balanced. My voltage equation will not be balanced. Why? Because my all the three phase voltages, right, will be sum of a zero sequence component and the fundamental component. So fundamental component although will be balanced, but there will be a third harmonic component, right, that will make the neutral, all the sums of the voltage not equal to zero. So there will be some voltage here. So neutral will not be purely at the center. Okay, that is a disadvantage. You can go through and read through all these things, what happens if I connect the neutral and all those things. Okay, so yeah, so that is a problem. So what is the problem in star-star connection? So there will be problem of insulation breakdown. Same thing is written over here. So while connection ensures perfectly sinusoidal flux, stable secondary voltage, it has drawback. The neutral wire. So in this case, now what is the problem with this one? If I don't connect neutral wire, then there is problem of then there is problem of insulation failure. If I connect the neutral wire, then what is the problem? If I connect the neutral wire, then I will come to that. Let me come to this one. So the neutral wire carries 150 hertz current, 3 times the third harmonic current in each phase. So the neutral wire actually carries 3 times the current in each 3 phases. So the neutral wire must be thick. So let's assume that if the maximum value of the third harmonic current is 10 amperes, so the neutral wire has to carry 30 amperes of current. So the neutral wire must be thick. Huge current is flowing through that, right? That is a problem. This can interfere with communication lines. So in case of transmission lines, right, if I have 2 wires, let's say this is the neutral wire, and let's say this is some transmission line through where you like phone call and do those things, right? This is communication line. Okay, now communication lines, what happens if there is huge amount of current flowing through this, right? Let's assume 30 amperes of current flowing through this sinusoidal. So it will generate a flux or magnetic field, and that magnetic field will interfere with this. It can change this current. It can add noise here. It can add noise, and due to that what will happen is that when you say hi there, that guy might listen something else. He might hear something else, right? Hi, something like that, something like that, right? So that is the problem. If huge current is flowing through the neutral, that can interfere with the nearby communication lines. So this is also a not very good solution. We don't like this. We don't like this kind of solution. Okay, so that is a drawback here. And let's see one more thing, comparison with single phase transformer. So in single phase, if you apply purely 50 hertz sinusoidal voltage to the primary, this forces the flux in the core to be purely sinusoidal only. Okay, however, due to core non-linearity, the magnetizing current still contains third harmonic component. So this we have already discussed. But in 3 phase, there is no need for special neutral connection. If I just want to keep the neutral open, the phase line voltages will be free from harmonics. The third harmonic currents can circulate locally. How? In delta connection. We will discuss in delta connection. This should have been in the first slide actually. Comparison to 3-phase transformer. I should have put this in the first slide actually. Here. Yeah, this will be the best place to put this, not here. Only here. Yeah, so I'm just comparing between single phase and 3-phase transformer. So for delta connection, there will not be any need of neutral connection. Delta connection, the third harmonic current will flow locally in the transformer only. It will not flow through the neutral wire. Okay, just like star connection. That's why we very rarely use star connection. Transformer self corrects the third harmonic voltage, we will see, because as there is a path for the third harmonic neutral current to flow. Hence the transformer, the induced voltages will be purely sinusoidal. Okay, so that's why 3-phase transformers are used, also due to this reason as well. Okay, of course there is advantage of high power transfer. This is also another advantage. Got it? Understood? Okay. Now one more thing you have to keep in mind in this kind of cases, right? In this kind of cases, one thing you have to keep in mind here, right? Why did it go? So this we have already discussed. So in this kind of cases, as the induced EMF will contain harmonic, so I cannot always use this formula. I cannot always use that my line to line voltage will be √3 times V phase. Okay, not always. Okay, not applicable, because although the triplet harmonics are getting cancelled, but there are 5th harmonics, there are 7th harmonics, like things will be messy. Okay, we cannot use this formula due to harmonics. So just be careful when things contain harmonics. You cannot simply cancel out. You have to use this fundamental equation. What is the fundamental equation? This one. Where did it go? This one, right? This equation derived from basics. Okay, understood? Okay, great. Now let's move on to the next thing. So I have not discussed about that the floating neutral kind of thing, right? I have not discussed about that. So now what is the problem here? The problem in, if I now connect both the neutrals to ground. If I now connect both the neutrals to ground, what will be the problem? So yes, now there is path for the third harmonic component, right? Now my magnetizing current, exciting current will contain third harmonic component. Im magnetizing current will contain component. Okay, so if magnetizing current contains third harmonic components, that means magnetizing current will be peaky in nature. This we have already discussed, and hence my induced EMF or flux will be purely sinusoidal if both the neutrals are connected. But again, there is disadvantage of this, right? EMI we have already discussed is the disadvantage of this, so that's why we will not use this sinusoidal. So what is the disadvantage? We have already discussed the disadvantage. As the EMI, that is the disadvantage. Okay, okay. So yeah, now the same thing whatever we have discussed is written over here, like in text, that okay, it is not written, we have already done it. Okay, we have already finished it. So now let's discuss about uh, delta delta star connection. Let's discuss about delta star connection. What will happen to delta star? So if I have a delta connection, right? If I have a delta connection, a circulating current will flow in the phases only. It will not flow in the line. Why it will not flow in the line? I will explain. If I have a delta connection, why it will not flow in the line? I will explain. So the figure is not drawn here. Okay. So let me first solve it. Right. I will first solve it. So let's assumption is our induced voltages contain third harmonic, right? Assumption is our induced voltages contain third harmonic. That is, so we write here induced voltages contain third harmonic. Okay, so if induced voltages contain third harmonic, then I can do one thing. Let me find out the current due to the third harmonic. Let me find out the current due to the third harmonic. So how will I find out the current due to the third harmonic? So one thing I can do is I can directly write this. So if I convert this circuit, right? If I just convert this circuit into this circuit, that I am just calculating the current due to the third harmonic induced voltage, because I know due to the fundamental component the current will be simply pure sine only. The current will be simply pure sine only. I just want to calculate the current due to the third harmonic component. So if I find out the current due to the third harmonic component, so let me delete this. So there will be some induced voltage, okay, that is same phase, right? Let's assume it as E3M, and the coil will have some coil will have some third harmonic impedance, right? Okay, So let's assume like third harmonic impedance also will be same only. Let's assume it has Z3, Z3 and Z3, and this is E3M. So one thing I observe, this is a closed loop, right? And I know that both of them will be in same phase. So if this is dot, sorry, let me just delete these things. So if this is dot, then this will be dot, right? And this will be dot. Okay. So if I simply, like, this will be, if I assume dot to be positive, instantaneous polarity, plus minus and plus minus. So if I apply a KVL in this loop, a simple KVL in this loop. So if you observe, if I apply a simple KVL, and let's assume there is some current, right, through this, okay, and by symmetry, what I will observe, that whatever the current flowing through here, same current will come out through here, IC, circulating current, and same current will come out through here, IC, circulating current. Okay, through symmetry I can say, because all these voltages are same, these impedances are same, so whatever current will come out, same current will flow through this loop only, none of the current will flow through here. How can I prove it? Yeah, my recording just got stopped. I just was saying that if you don't agree, sir, I am not agreeing with you. Sir, whatever you are saying that this circulating current due to the third harmonic is flowing only in this loop, you are incorrect. I don't believe you. I believe that third harmonic current will flow in this line as well. Okay, I agree with you. Let's take a small example. Let's take a small example that let's assume that this is phase some A, right? Phase A. So IA current is equals to, it contains a combination of the fundamental and the third harmonic component. So it will be IA1 plus IA3. So it contains IA1 plus IA3. And let's take this current, right? Let's assume this has some phase current B, IB is equals to IB1, the fundamental component, and the third harmonic component, IB3. Okay, so it contains both IB1 and IB3. Now, the interesting fact to note here is that what will be the current IA? IA will be a subtraction of this current. Sorry, if I write the KCL equation, so IA minus of IA minus of, okay, this is not, let's assume this is line current only. Let me write this as IAL, else you will get confused. So minus of IAL will be equals to IA minus of IA and plus of IB, correct? So same thing, right? Whatever was we were doing for the phase voltage there, same thing is happening. What, that the line current is subtraction of the two phase currents. So the third harmonic component will simply get cancelled, only the fundamental component will be left out. So same conclusion, right? So again, I told you third harmonic currents will not be there in the line. So conclusion is line will not contain any third harmonic. Current. Line will not contain any third harmonic current. That's it. Okay. So as we were discussing that, now let's come to the fact. So let's assume that there is a circulating current, that is the third harmonic current, that only flows through the phases. Okay. So now if I apply KCL here, you will observe that minus EM minus E3M minus E3M minus E3M plus IC into the impedance, right? So there are three drops here, Z3. So it will be 3 times IC into Z3. So basically what is happening, this circulating current is flowing only through the phases IC. Magnitude will be the third harmonic voltage by the impedance of the third harmonic, right, of the coils. So the thing is here is that actually I'm not suppressing any third harmonic current. So in the coils, third harmonic current is flowing. So the conclusion is, in the coils, third harmonic current will flow. And if third harmonic current is flowing in the coil, so current is more peaky, right? So current will be more peaky, phase current will be more peaky. So if phase current is more peaky, then the flux, induced EMF, flux will be more sinusoidal. It will move more towards sinusoidal. It will be more sinusoidal. That is the conclusion in delta. So my third harmonic currents are also flowing. There is no third harmonic currents in the line, so there will not be any interference in the line, right? No interference in the line. Third harmonic current is flowing, okay, and so my flux is also purely sinusoidal. It is just like a very good husband. A very good husband will agree with his wife, will agree with his mother as well. Okay, so husband has to be very balanced. He cannot disagree with his wife. He cannot disagree with his mother as well, right? He has to keep everyone happy. So what happens in delta? Delta keeps the circulating current happy. So, like the third harmonic current says, I want to flow third harmonic, right? Like to make the flux sinusoidal, we need third harmonic current. So delta says, no problem, I will let you to flow the third harmonic current through the phases. But there was a problem in the line, right? There was a problem in the line that if the current in the line, third harmonic currents flow in the line, there will be EMI. We discussed, right? There will be EMI here. Here there will be EMI, electromagnetic interference. Huge current will flow, or like there will be communication interference, right? So he has to like satisfy line current as well. So somehow we do the calculation and the third harmonic component gets cancelled out. So that is a quality of a very good husband. Okay, I hope whoever is watching, the girls who are watching this, they will get a husband like this also, because of course of course I do understand your husband needs to agree with you as well, but he has his mother as well, right? He has to agree with her as well. Okay, just don't take it lightly, just take it as a joke. Okay, don't take it seriously. Okay, got it. So my flux will be purely sinusoidal, more sinusoidal, more sinusoidal. Okay, so that is the conclusion basically, whatever I discussed, that a third harmonic current will flow I3, circulating current. The magnitude will be this E3 by Z3. This circulating third harmonic currents remain confined within the delta loop and do not appear in the line currents. As a result, the line and phase voltages remain totally free, because what is induced EMF? Induced EMF will be purely sinusoidal because the flux is sinusoidal. So as flux is sinusoidal, just hold on, as the flux is more sinusoidal, so induced EMF will also tend to more sinusoidal. So my induced EMF E will also tend to more sinusoidal, not purely sinusoidal, because if induced EMF is purely sinusoidal, again there will not be any third harmonic current, right? How is it possible? But it will tend to more sinusoidal. So induced EMF will tend to more sinusoidal. That is the main advantage, main aim. Okay, so yeah, that is the case over here. That is the advantage. You can go through this. So this inherent ability of delta configuration to absorb or trap the third harmonic currents is one reason why delta windings are often used in transformer connections. Everybody will see, mostly will use delta star or star delta. Delta will always be there. That is the sole advantage of this delta connections. Okay, so now what happens if, even though my connection here, right, is star connected, even though like I know there will be some third harmonic components, Due to the third harmonic currents, the induced voltage will be purely sinusoidal. As the induced voltage here is purely sinusoidal, here also as the flux is purely sinusoidal, so here also the induced voltage will be purely sinusoidal. There will not be any third harmonic current in the secondary. Okay, there will not be any third harmonic current in the secondary. Got it? Even though there is third harmonic current here, there is no third harmonic current here. Why? Because here the flux is purely sinusoidal. Due to that, the induced EMF here also will be purely sinusoidal. Got it? So yeah, those are few conclusions. So let me go through, read this. So same thing is written over here. Delta provides loop, all those things, no need of. So in delta, right, there is no need of external neutral connection. So here, right, I don't need to connect the neutral here, because here my flux is purely sinusoidal and the same flux will flow through this winding as well. If the same flux is flowing through this winding and if it is sinusoidal, so it is sinusoidal. So the induced EMF here, induced EMF E also will be sinusoidal. E also will be sinusoidal. Okay, that is the case over here. I hope you have understood this one. Okay. So this was about the delta star connection. This was about the delta star connection. Now delta star, in the delta side, any third harmonic voltages generated by the core flux create circulating currents within the closed loop, and due to that, so even though there is, let's assume that there is a third harmonic voltage. So if there is a third harmonic voltage, what will happen? A third harmonic current, circulating current will flow. Due to the third harmonic current, that will oppose the third harmonic voltage. So internally, delta has a self-correcting loop. Okay, so that makes the induced EMF more sinusoidal, and if it is more sinusoidal, it will make the secondary also more sinusoidal. Same thing is written here. So this circulating third harmonic current I3 suppresses the corresponding harmonic voltages. In these voltages E, this results in sinusoidal EMF on the star side, while the current may show flat top behavior due to suppression of third harmonic currents, third harmonic voltages. While the current, so the current here, right, will be bit peaky in nature in the delta connection. Okay, so basically in case of delta star connection, the advantage is whatever third harmonic induced voltages will be there, this delta will automatically oppose it. That's why delta connection is very, very important. Okay, that's why delta connection is very, very important. Now let's come to the delta star. Let's come to the star delta. So what will happen in the star delta? So again the same thing, right? Again the same thing. So here, right, it is not connected. This is not connected, right? It is not grounded. So here I know the magnetizing current Im will be purely sinusoidal. Magnetizing current Im will be purely sinusoidal. So if magnetizing current Im is purely sinusoidal, then what will happen in the secondary? So my flux, right? My flux will not be purely sinusoidal. In the primary side, it will say the flux phi is not purely sinusoidal according to the star connection, not sinusoidal. But if flux is not sinusoidal, then there will be third harmonic components here. The induced voltage will not be purely sinusoidal. Not sine. E induced is not sine. So E induced is not sine. So if E induced is not sine, right? If E induced is not sine, that means what? There will be third harmonic circulating currents in this delta loop. There will be circulating current IC in this delta loop. So if there is circulating current IC, that will what? That will oppose the third harmonic induced EMF. So that will oppose the third harmonic. That means it will try to make the flux phi sinusoidal. So ultimately there is fight between husband and wife. Someone has to agree, but both ultimately come to a common conclusion, right? Husband also does not get his complete wish and wife also does not get his complete wish. They both sacrifice a bit and come to a conclusion. So here also same thing, that first there was fight because current is purely sinusoidal. If the magnetizing current is purely sinusoidal, we had already discussed that flux will be flat topped. Flux will be flat topped. So if flux is flat top, your induced EMF also will be flat top. So in the secondary delta as well, the induced EMF will be flat top. So if the induced EMF is flat top, then what will happen? A circulating current will flow. Due to the circulating current, it will oppose the third harmonic components. So as it opposes the third harmonic components, so the flat top or not sinusoidal component of the flux reduces. So ultimately my flux tries to be more sinusoidal. Flux tries to be more sinusoidal. Okay, more sinusoidal. That is the advantage. That is the advantage over here. I hope you have discussed this very basic things. Okay. So yeah. So here as well, now you can do the self analysis, right? Here if I assume that my voltage is not purely sinusoidal, again if my voltage is not purely sinusoidal, so then what will happen? Third harmonic current will flow, circulating current. Due to that, it will oppose the third harmonic component. So automatically what will happen is flux will become sinusoidal. So if flux is becoming sinusoidal, then the secondary also will be purely sinusoidal only. Same analysis you can do. So now if some connection like this comes up, you should be able to theoretically say what will happen. Okay, that is the main purpose, right? That is the main purpose of this. So yeah, that's why I don't want you to muck things up, remember things up. These whatever points are written here, I don't want you to remember it. I want you to understand it conceptually what is happening. So in star delta connection, the delta secondary provides a closed path for circulating third harmonic current induced by a non-sinusoidal core flux. This allows the flux waveform to remain sinusoidal. It will oppose the non-sinusoidal component, induced EMF to be free from third harmonic distortion. Okay, so this delta acts as a natural harmonic filter. That is the advantage basically. So yeah, I hope you have understood this basic point. Now delta delta, again delta delta anyways, it will not contain any third harmonic component. Where is delta delta? Yeah, so before that, right? So what are the general guidelines basically for like this connection? So should star be connected in the high voltage or delta be connected in the high voltage? So generally what we follow, design, this is just a general rule of thumb, nothing fixed, that generally what we follow is that star is generally the connected in the high voltage side and delta is connected in the low voltage side. Now why is this the case? This is the case because if you see that the rating of the transformer is dependent on the coil voltages, right? And in case of star, the line voltage is root 3 times the phase voltage, and phase voltage is the voltage that is my coil voltage, correct? So to reduce cost in insulation, so my coil voltage will be what? Coil voltage will be VL divided by root 3. Coil voltage will be VL divided by root 3. Okay, this is what my coil voltage is. So I need less insulation, right? So that's why generally we connect the star on the high voltage side and delta on the low voltage side. Okay, so reduces the phase voltage, therefore insulation requirements is reduced, minimizes dielectric stress, same reason. Connect the low voltage to delta helps suppress the third harmony, because I have to include delta somehow, because as we are seeing the advantage of delta, it is helping us reduce the third harmonic issues. Provides path for the zero sequence or the circulating currents. Okay, hence generally the star delta configuration is used in power transformer. In power transformer where we are transforming power, so there star delta configuration is used. In distribution transformer, delta star is used. Why? Because in the secondary side must be a star connected, because if you see in the load side, you have a neutral wire. In your home you have a neutral wire that is generally connected to ground, right? So to get the access for the neutral, so the secondary is connected in the ground or neutral for a distribution transformer. Don't worry, we will discuss in power system as well. Okay, so one side you have fixed as star, that is a secondary. So this time the low voltage side will be the star connection. Why the low voltage? Because whatever voltages you operate in 415 or 230 volts, and whatever voltages, whatever power we transmit in high voltage, 3.3 kV, 11 kV. Why is that the reason? We will understand that in power system. Also, I have discussed, I think previously, why we transfer in high voltage. So this time the high voltage winding, we have no choice, it will be delta, and the low voltage winding, LV winding, will be star. So again, this can be asked in interview. Why am I telling you all this? Because these things can be asked in interview, that's why. So if they ask you why power transformer is star delta, will you be able to answer? Yes, you will be able to answer. You will say, sir, the high voltage side will be star because the I will require less insulation, and generally we generate in star configuration. The generators are also connected in star only, and there is neutral wire, so insulation requirements are lower. So that's why the high voltage side will be star connection, and the low voltage side will be delta, because I have to incorporate delta to remove the zero sequence current or the circulating currents. So for a power transformer, high voltage side star, low voltage side delta. For a distribution transformer, now as the distribution transformer will be connected to load, so the low voltage side will be going to load, and we know the load requires neutral. In your homes, there is a neutral connection, right? So as load requires neutral, so right now I have no other choice. I have to put the star on the neutral, on the low voltage side, and the high voltage side will contain delta because I have to remove the harmonics. Okay. So again, these are all interview things that can be asked. What about delta delta connection? Delta delta connection is pretty simple. Although we don't use delta delta connection. So both primary and secondary windings are closed loops, allowing third harmonic currents to circulate freely, no problem. Your core flux will be purely sinusoidal. Your EMF also will be purely sinusoidal, no doubt at all. There is no doubt at all. Okay. So just important point to note here is, even if one one of the winding is delta connected, then third harmonic currents will circulate in that loop, and due to that your flux or EMF, induced EMF, will be purely sinusoidal. Purely sinusoidal. Okay, got it. So like why do we want these harmonics to be removed? What are the disadvantages? So there are multiple of those. So I will discuss few. So one is increased ohmic loss. So due to the circulating currents, it will reduce the copper loss. In the neutral wire, 3 IM current was flowing. So what will be the copper loss in the neutral for a star connection? Okay, for a star connection I am discussing. So for a star connection, there was 3 IM current, right? 3 I3M current flowing through the neutral wire. So what will the copper loss? Copper loss will be IN whole square R or Zn, whatever, Rn, right? Neutral resistance. So it will be IN whole square into Rn. So this will be equals to 3I 3M whole square into Rn. So can you see how much, by how much the copper loss is increasing? It is like 9I 3M whole square into Rn, huge, right? So disadvantage. Another is electromagnetic interference. We have already discussed about this. Again, waveform distortion. Of course, the flux will not be purely sinusoidal. There will be a bit of problem if the induced EMF is contains star harmonic. We have already discussed about this, right? Insulation problems will be there. Core loss increase will be there, because core loss also will get added now. There is third harmonic component. Core loss will also increase. All this we have already discussed, right? So just giving you few things. Okay. So how do we suppress the harmonic? So one thing would be to operate at lower flux density, right? If I operate at lower flux density, then the chances of harmonic will be very, very less. Why? Because my B3M, right? The value of B3M will be very, very less. So core will not saturate. Why? Like, what was the problem of harmonic? The problem was what was the problem? Problem was core was getting saturated. Core was getting saturated. Due to this only the third harmonics came, right? If you remember at the starting, core was getting saturated. Core was getting saturated. So if core is getting saturated, what I can do is, if this is my BH curve, right? This is my BH curve. I will operate in this region. I will not operate near here, right? I will not operate near here. I will operate near here, operating region. So then there is very less probability of core getting saturated and the waveform getting flat top or something like that. right? What is the disadvantage? The disadvantage, if I am fixing my BM, if my BM is getting lowered, there are two ways I can reduce my BM. One thing is, what is BM equals to? BM is equals to phi by area, right? So either you reduce the flux. Now if I reduce the flux, right, so the induced EMF also is getting reduced, because flux is basically proportional to induced EMF. So I cannot like transfer huge amount of EMF. That is a problem, right? Cannot transfer voltage. I want to let's say I want to design a 11 kilovolt transformer. I cannot do it, because if you are limiting the flux, right? Limiting the flux means limiting the voltage. Or what you can do, you can increase the area. If you increase the area, then also the flux density will reduce. Again the same problem. If I increase the area, the size of the transformer will increase. So not a very good solution, right? Like it will cost more, it will consume more size, not a very good solution. Another solution we have already discussed is delta connection. Either you connect the delta in the primary or secondary, it will automatically totally remove the third harmonics. Also the best way is to use a star delta connection that we have already discussed. So star star connection does not provide any path for the zero sequence currents if it is neutral ungrounded, but if it is grounded it does provide, but there are problems for losses as we have already discussed. But for delta star delta connection it is totally fine, we can use. So we can use a tertiary transformer, okay, where we will have a delta uh, connection that will totally remove the circulating currents. That is what we will discuss here. So what we will do is we will have a transformer. Let's say you are saying that, sir, I want to use star star connection only. Sir, I want to use star star connection only. No matter what, I will use star star connection only. So what we will do, we will connect an extra additional third winding in the core known as tertiary winding, where it will be delta connected. So the tertiary winding will be connected in delta, and this will, let's assume this as the supply, start as the supply, and this as the load, this as the load, and this also as the load. Okay, so both of these two are load only, both of these two are load. So what will happen is that you balance out the mmf, whatever you want to do, okay. What will happen, this, right, this delta will help reduce the third harmonics. Okay, this delta will help reduce the third harmonics. So one thing we have to notice here is that it is actually open here, right? It is not connected, it is open. So if it is open, right, only zero sequence current can flow. Why? So let's assume a case. Let's assume that if my load is balanced, if my load is balanced, if my load is balanced, then I know like it will induce a current that will be 120 degrees phase apart. It will induce a current that will be 120 degrees phase apart. Okay, if it is 120 degrees phase apart, and you say that in the tertiary also a current will be induced that will be 120 degrees phase apart, right? Current will be there that will be 120 degrees phase apart. Is it possible? What I am saying is whatever current is going through here, same current will flow through here, right? Because it is open ended. So it is not possible, right? Not possible, because this current is same as this, but here you are saying that yeah, magnitude is same, but they are phase shifted by 120. Not possible. So I can safely say that in tertiary winding, tertiary winding, in tertiary winding only zero sequence current can flow. Okay, so in the tertiary winding only zero sequence current can flow, and what is the advantage? This circulating current will actually make the will this will help this will help in making the core flux more sinusoidal. Okay, that is the advantage here. Now you might say, sir, here some zero sequence current is flowing. Sir, here some like purely sinusoidal current is flowing. How is it possible? So there will be MMF balance equation, and the primary will help in MMF balance. Okay, primary side will balance the MMF. Okay, MMF means the magnitude of multiplication of current and current and the number of turns. Primary side will balance the MMF. Okay, primary side will balance the MMF. Okay, got it. So the main thing is that if my load is unbalanced, so if it is balanced, then there is no problem. If it is balanced, if my load is balanced, right, then the tertiary will not carry any current. Then the current IT will be zero because load is balanced, flux will be balanced, everything will be balanced. If somehow my load is unbalanced, if somehow my load is unbalanced, if somehow the load is unbalanced, then what will happen is that there will be three sequence of current, right? Don't worry, we will discuss this in power system analysis. One will be the positive sequence current, that is the balance side of the things, and the second one will be the negative sequence current, that will also not flow through the delta winding, that will flow through the star only, and the third one will be the zero sequence current. So this zero sequence current, this will not, this will help, like this zero sequence component of the current, the delta winding will help in cancelling this one out. So the tertiary winding will help in removing this harmonic. Don't worry if you don't understand what is positive negative, we will discuss this in power system. Help in removing this harmonic. Okay, tertiary winding will balance the MMF and it will remove this zero sequence current. Other currents will be there. Okay, those we will discuss about other things, but zero sequence will be totally removed by the tertiary winding. So that's why we use this tertiary winding to help us remove these components. So that was about the star-star configuration. So in case of star-star configuration, we use a tertiary winding, a third winding, which is delta connected. So the third winding connected in delta is added in the same magnetic core. It provides a circulating path for the third harmonic magnetizing current to make the flux waveform more sinusoidal. Voltage waveform remains sinusoidal, system remains balanced under asymmetrical or unbalanced loads. Even though load is unbalanced, so we are removing the zero sequence component. So negative sequence components will be there, but the magnitude may be lower. Main component will be third harmonic component, which is a zero sequence current. So we are actually removing that. If we are removing that, my flux will be more and more sinusoidal. So the induced EMF also will be more and more sinusoidal. So that is the advantage of a tertiary winding. So this is mainly theoretical points. So in some systems, tertiary winding can be loaded to like allow our transformer to work our transformer in different voltages. Let's say if this winding was supposed to work in 10 kilovolts, this winding is, let's say, some other voltage level 6 kilovolts, 6.6 kilovolts. So we can use the tertiary winding as well for connecting a load, but generally we keep it open. But just in case if we want to, we can use it to connect a load as well to work our transformer in different voltage levels. So that is also another advantage. Okay, so tertiary winding provides many flexibility. It provides flexibility in voltage level, it provides as a backup supply option, also it provides in balancing the supply. Okay, so last thing is there about zigzag, that same thing only I will discuss in zigzag. Same things I will discuss in zigzag is that in zigzag, in regular star-star connect transformers without delta or tertiary, third harmonic currents cannot circulate, but third harmonic flux is generated in the core. This induces third harmonic voltages in the windings. Okay, however, now if I connect this star-star in zigzag, right, however, due to zigzag structure, these voltages are co-phasal, same phase. When added, they cancel out. So what do I mean? So even though I know in case of star connection, that now we are discussing about zigzag, how in zigzag connection the third harmonic components are suppressed. Okay, now we are discussing about the zigzag. So in zigzag I know, sorry, in a star connection I know that phase voltage might have a third harmonic component. Let's say that the phase voltage has a third harmonic component, VA equals to VA1 plus VA3. Now in zigzag what happens? The phase voltage is not VA, it is VA dash, and VA dash is combination of two phase voltages which are half of each other. So VA dash is VA by 2 and VC by 2. This we have discussed in the three-phase transformer lecture, right? What happens, what is the advantage is that the phase voltage actually VA dash is free from third harmonics. Why? Because again I am doing some subtraction, so the common component will be cancelled out, so the zero sequence component automatically gets cancelled out. So that is the advantage of a zigzag. So that's why zigzag also is used if I don't want to use delta connection and I want star only, so I will use zigzag connection. So that will help us remove the harmonics. So very important point, how does zigzag connection remove the harmonics? Okay, so zigzag acts as a natural third harmonic suppression, making it superior to simple star-star. So we generally never use simple star-star connection. We either use star-star with tertiary winding or star-star that is zigzag connected. That is the best way to use star-star connection if you want to use star-star only. Okay, that is the advantage. So that is one thing. So that's why zigzag is used. You can go through and read over this. So I hope now you understand why each connection is used and why I don't use some connection. Why I don't use star-star connection. Why I use delta-star. Why delta is used in the high voltage sometimes. Why is it used in the low voltage? Why star is used in the high voltage? Why star is used in the low voltage? So you should ask why and where should I use these connections. So I have given you the practical reasoning why each connection is used where. Okay. So before finalizing in the real world, I've given you the feel why this is delta star, why this is star delta. So in the interview, if someone asks, all your answers will be clear. So we have covered every single thing, the interview portion, the theoretical portion, the numerical portion. So nobody will be able to beat you, trust me on this. Okay. So yeah, same thing we have discussed here. So summary, you can go through this, you can read through this, no problem. Okay. So now let's do few questions. Okay, few theoretical, mainly GATE also has asked portions, but very rarely they have asked. But like it will be very easy question. Trust me, it will be very easy. Okay, it will not be very hectic for you. Okay, so yeah, let's discuss this question. So a single phase air core transformer, air core means it does not have any saturation, no saturation, right? Air core means it does not have any saturation. Fed from a rated sinusoidal supply. So supply is sinusoidal. That means the voltage is sinusoidal. Voltage is sinusoidal. If voltage is sinusoidal, what will be the exciting current? Exciting current will be what? Is operating at no load. The steady state magnetizing current drawn by the transformer will have the waveform. Will the exciting current be peaky? If you answered the exciting current will be peaky like this, right? It is peaky here. It is peaky here. So if you answered this, you are very wrong. You are wrong. Why? Because in the starting of this lecture, I had discussed three cases where the core was not saturating and where the core was saturating. In this case, the core is not saturating. If it is not saturating, there is no question of harmonics. There will not be any harmonics because core is not saturating. I have discussed this. Please go through at the starting of this lecture. I have discussed this. So here, as the core is not saturating, hence the current will also be purely sinusoidal. If voltage is purely sinusoidal, current also will be purely sinusoidal because the core is not saturating. If the core is supposed to be saturating, then it would have been peaky. Then the magnetizing current would have been peaky. Okay, please don't mug things up. Okay. Now let's discuss this. How do harmonics influence the performance of three-phase transformer? What design strategies are used to counter these effects? So again, we have already discussed like how does harmonic influence, right? I know the current contains now two components. One is the fundamental component, another one is the third harmonic component. Then we have fifth harmonic component, seventh harmonic components. Odd harmonics we only have, we don't have even harmonics. This you will learn in Fourier series. So what will be the RMS component value? So all these are different frequency components. So RMS values will simply be squared and under root. So it will be I1 RMS whole square plus I3 RMS whole square plus I5 RMS whole square dot. Okay. So yeah. So again, your current IRMS is increasing, right? Previously, your IRMS was supposed to be I1 only. Okay, now your IRMS is combination of all this, so it will only increase. So if your IRMS has increased, that means your losses will increase because what is it? What is the losses? What is the copper losses? Copper losses is simply IRMS whole square into R. Correct. So if IRMS whole square into R has increased, so your copper losses PCU will increase. Again, coal loss also will increase, right? We have already discussed coal losses also will increase because it depends on frequency component. So coal losses will also increase. So it will heat the transformer more. Heat also will increase. So transformer efficiency will reduce and it can get damaged easily, and aging also will happen faster. Aging also happens faster. Okay. So these are the like answers. What does harmonic cause? All those things. Okay, and how we can mitigate it? We can use delta connection, delta connection to remove the harmonics. We have already discussed. So that's it basically. That's the end of a transformers chapter. It was a big chapter and the last lecture was very big. I hope you are able to bear with me till then. If you are able to bear with me, please do comment below. Yes, you watched it till the end, and make sure to go into the first video. Please put a review, whatever you felt like. You hated something, you can write that. You loved something, you loved the concept, you can write that. Trust me, whatever you have learned everything. Okay, in no other place if you go, you will not find a single point that is not present in this notes and in their notes. Okay, whatever you will learn the most maximum that you can learn, right? Trust me, if you are preparing for gate, whatever I have taught you is the maximum that I can teach you, right? No one knows more than you. Now it's up to you how you can deliver it. Okay, so everything we have learned conceptually, and I have written everything. I have told you how delta connections was, all those things, right? So yeah, that's just the first chapter. Now we will come to more interesting portion. We have second chapter, DC machines. So in the next lecture we will start with new chapter, that is DC machines. So if you enjoyed, make sure to like the video, comment down in the video, and I will see you in the next lecture. Until then, happy learning.